To move something heavy across a room, you have to physically push it. The second you stop pushing, the object grinds to a halt. We spend our entire lives fighting friction. This daily experience conditions us to assume that sitting perfectly still is the natural, default state of the universe. This assumption was so convincing that ancient Greek thinkers like Aristotle built their physics around it, arguing that motion requires constant effort to maintain. To understand how the universe actually works, we have to look past what our eyes see on the surface and account for the forces we cannot easily detect. Consider a heavy textbook sitting undisturbed on a desk. Compare that book to a car cruising down a straight highway at a perfectly steady 60 kilometers per hour. Finally, look at a space probe with its engines powered down, drifting silently through the vacuum of deep space. To our eyes, these three objects look like they belong to different worlds of physics. But despite their different speeds, they all share a single, hidden mathematical property. Physics focuses on the invisible balance of forces acting upon an object, rather than its velocity alone. This balance is defined by Newton's first law of motion and the concept of net external force. This diagram shows the forces acting on a resting book. Gravity pulls downward. The table pushes back up with equal force. Because these opposing forces cancel each other out, the net external force is zero. Zero net force means zero acceleration. Now look at the diagram for the cruising car. The engine and tires provide a continuous forward push. At the same time, road friction and air resistance pull backward on the car with the exact same amount of force. Like the resting book, the pushing and pulling on the car cancel out. This proves that uniform motion is a state of zero net force. What happens when that balance of forces is broken? Imagine a passenger holding a stone out the window of a train that is accelerating down the tracks. While held, the stone shares the train's acceleration because the passenger's hand applies a direct physical force to it. This diagram shows the second the stone is released. Instantly, the horizontal forward force disappears. The stone carries no physical memory of the train's acceleration. Only the downward pull of gravity remains active as it begins its curved descent. An object's physical state updates instantly. Acceleration exists only in the exact moment a net force is being applied. You experience these mechanics while standing in the aisle of a stationary city bus. This is inertia, an object's resistance to any change in its current state. As the bus accelerates, friction between your shoes and the floor pulls your feet forward. Because no immediate force pulls on your upper torso, inertia keeps it still. You fall backward relative to the moving bus. The process reverses when a speeding bus suddenly brakes. Friction stops your feet, but your upper body is already in motion. Your inertia maintains that motion, causing you to stumble forward. That feeling of being jerked around on transit is the physical result of your own mass. Your body maintains its original state, while the floor of the bus shifts beneath it. This connects the resting book, the cruising car, and the deep space probe. Newtonian mechanics describes a universe that defaults to the status quo. Matter maintains its current state until an external force demands a change. Motion itself does not require a cause. Only a change in motion requires a force.